Are we ready, Nicholas? Okay. So I had mentioned the King Street Bridge failure in Melbourne, Australia, and I was looking through a book on design of weldments for this course and came across the design that caused the failure on the King Street Bridge that I mentioned before. And here's the girder, which is holding up the bridge, and it was a very big girder. I mean, they didn't give me the dimensions here, but you had a plate and another plate, and they basically put fillet welds along here. And so on one side you have a fillet weld, and on the other side they had what they call a doubler plate. You need a little more stiffness on the flange, so they put a doubler plate on. And I had mentioned to you they had welded all the way around. I had remembered that. But basically, this is like a cruciform joint almost. You've got two welds on this side. You've got this very stiff, very thick plate. You've got a lot of restraint here. Nothing can bend or bow or very much. And they put this weld across here. Well, this weld across here was doing nothing. It wasn't carrying any load. Okay? And so that's why today the codes don't allow you to wrap all the way around, because usually it's not adding any strength. It might be convenient for some things, but in any case, they wrapped all the way around. They got a hydrogen crack because of all the restraint at that location, and that grew over time in fatigue because it's on the tension side of the beam, and eventually it got long enough and you got a brittle fracture, and the bridge came down, and people all over the world were upset. People don't like bridges falling down. Okay, so that just illustrates some of the things that we've been talking about. Getting back to aluminum, we've talked about non-heat treatable aluminum alloys, kind of the 5000 series, and a few others. But it's not too hard to have enough alloying element in the weld metal that when it solidifies, the weld metal has sufficient alloy addition that you can get 100% joint efficiency. That means if you make a tensile bar, it will fail on the base material and it won't fail on the weld metal. You get equal matching or overmatching weld metal, which is what you usually want. Okay. Then there's the heat treatable aluminum alloys. The difference here is these alloys might be 30 KSI type of strength. These can be 50, 60, or 70 KSI strength. There's double the strength, but the precipitation, the heat treatable ones are precipitation hardens, which means when you heat them, the heat of welding overages the material in the heat affected zone. You lose your strength, and if you actually plot the hardness across the weld, so this will be the weld, this is the hardness, weld, heat affected zone, and base metal. So you do a micro hardness traverse in the weld, you can alloy, make it fairly strong, and then in the heat affected zone you're going to have a softening, and in the base metal you'll have reasonable strength. So you're going to get softening, and you can only lose 40% of your strength. And so you don't get, if you're using a strength limited design, you'd lose the advantage of the heat treatable alloy. So we have to do some things to take care of that, and there are a lot of things that the people in aluminum do to try to make it possible to weld and take advantage of the high strength of the heat treatable aluminum alloys. But in addition, I had mentioned to you that aluminum alloys tend to be prone to distortion and high residual stresses because aluminum has a 6% volume shrinkage on solidification. And so they do a lot of things to try to reduce the stresses at the welds in aluminum, more so than we have to fool around with in steels most of the time. So here's an example out of an aluminum design handbook where I have two different thickness plates. And in this case you make the weld, but you also taper the thicker plate rather than just having, you saw on the King Street Bridge, that they basically don't do anything, just have a square end of the steel, which creates a stress concentration. To alleviate the stress concentration on aluminum, because it's easier to machine, we'll often bevel that joint so it tapers down to get a more uniform stress distribution across that joint, okay, to improve fatigue resistance. And fatigue resistance is more of a problem in aluminum alloys than steel. Steel has a fatigue limit. Aluminum doesn't at high cycles. Now another thing that they do, this is, instead of trying to weld two plates together because you can't get full strength, you sometimes can put two plates on top of each other, and this is, they call it a practical design. It increases the weight, it messes up the geometry of the whole structure. You may not always have time to do it, but essentially you can put a lot of weld metal in if you get a lot more area than you get with just a simple little seam between two plates, like we do as a butt weld in steels. This is not a good detail, even though you don't need all the weld metal that's over here at A. In D, you end up with ends, and I'll show you later, the ends of the welds often have their own types of stress concentrators. You can do it on just one side of the plate if the loads aren't very heavy. You can do a really nice one, it costs a little bit more, where you bevel the edges and distribute the stresses, or you can just simply overlap the two plates and put a fillet weld on either side. So you actually get essentially double the weld in a lap joint like this. As long as you're not going to be worried about a fatigue crack running down this little slot that you have between the two plates, or corrosion that might get in there or something like that. So there's a lot of different designs that people fool around with. I'll show you some more here of how we pay more attention and spend more money in aluminum, but there's a reason why we can spend more money in aluminum. Anybody know? Those of you that took class last semester? It's lighter, but it's also more expensive. Aluminum is about 5 times the expense of steel, so they're always more expensive structures. Okay, so you can afford to spend more time worrying about the joints because you've got inherently a more, remember I talked about the value of a pound saved in an automobile is $2 a pound, and an aircraft is $200 a pound, and a spacecraft is $20,000 a pound. Well, aluminum structures are 5 times the cost per equivalent volume or size as steel, and therefore you can fool around a little more with forming or machining your edges and prepping them and whatnot. And you need to. But here's a way to look at, you're trying to make some sort of box section with an enclosure. Well, you can't make this one. You don't have access inside to get in there to weld that. You can design that on a computer, but you can't make it in practice. Okay? So here's one where instead of having it over the U-shaped piece overlap, you have it as an internal insert, and now it's recommended, although you might end up leaving these off and just having the top two without the bottom two, because even these might be hard to get at. The inaccessible ones over here are really hard to get at because you got to kind of turn the corner. Here you might be accessed from this side, but there might not. But a simpler one is to get rid of half the welds by just forming the whole thing. And aluminum is relatively easy to form compared to steel, so far as that goes. Here are some things where they basically scarf the joints and make overlaps and try to make simple fillet welds as opposed to butt welds and things like that. Here's another one down here where you see they have a fillet weld over here. They basically have a curved joint. You can have a lot of aluminum extrusions and stuff that you can't afford to do in steel with its high melting point. And they actually machine the edges to make a nice bevel to get better penetration. Yep. Potentially, yes. You could, yes. Okay. I mean, it depends. Yeah, it depends on what you're doing, what the required stresses are, and things like that. But I mean, actually, as I look at that, I don't think that's as good as an example as when I just copied it out of the book. Okay. Now, well, here's some other joint designs of just intersections. This is kind of sheet metal welding, simple butt joint, fillet joint, T-joint. Here you got a corner joint, but you might want to try to get both sides. The lap joint again you form and you make a weld up here. If you have access to the backside, you can put a weld underneath there and you get double the weld. If you're doing heat treatable alloys in aluminum, you may have to do such things. Well, I didn't talk to you about the air tanks on the cement trucks, did I? I think I might have. Well, let me tell you the story of that. So they're aluminum. This is an aluminum tank weld. Here's the dome on the end. Here's the cylinder, and they put a backing bar in here. This is typical, so that you can put the weld from the inside because it's circular. I mean, from the outside because it's circular. You could do things like this. This is a simple butt weld like we'd have in steel with no problem, but in aluminum you're liable to use a sleeve and essentially double the welds, okay, as a sleeve on the outside. But on this one, basically it's just a simple tank and cylinder, and there's a story that goes with this type of joint. There was a company that made cement trucks. And if you drive around a cement truck, when you deliver your cement, it splatters all over everything, including the cement truck. And so they carry about a 200-gallon tank of water on the cement truck with a little hose, so you can hose off the cement that you spill on everything. They also typically carry a gallon or two of sulfuric acid or hydrochloric acid, muriatic acid, because that's even better at removing dried on cement, okay? Except it's a little corrosive so far as that goes. So they don't carry that much of it. But muriatic acid is a thing that you go to the hardware store and it will tell you it's something used to clean cement. Why? Because hydrochloric acid will react with the calcium carbonate and allow you to dissolve it so far as that goes. I had a situation once where a cement truck was coming through Connecticut, going over a bridge. All of a sudden the guy lost his steering and drove the cement truck off the bridge and killed himself, okay? And the truck wasn't in very good shape either. You know, take 60 tons off a bridge and drop it 100 feet, you know, it's not good for the truck. And the question was, why did he just drive off the bridge? Well, it turns out in the steering gear, it basically had some gears and they had corroded because he had been using the muriatic acid to clean off the underside of his truck, and he had been dissolving away his gears. Okay, some of the stuff was leaking through the seals and stuff, and you know that's why he lost his steering. So anyway, on cement trucks you have to clean things off. They try to use water. Certainly when cement is wet and hasn't hardened, you can use water. It's only when it's hardened you have to use the muriatic acid. So in any case, they had these 200-gallon tanks that they were going to put on these cement trucks. They want to keep the weight down, even though you're carrying all this heavy cement. There are load limits on the highways, and so they wanted to make them out of aluminum. Okay, so this company, very big company, made military hardware and stuff, but in fact, they kind of went around buying up little mom and pop vehicle manufacturers. A little company over here in Wisconsin might make fire trucks. They buy the basic truck from General Motors or Ford, which is just the cab and the steel beams, and then they just slap on some back end of the truck and turn it into a fire truck, okay, and sell it for $200,000. Another one builds ambulances. Another one builds police cars, or modifies cars for police cars. Another one builds cement trucks. So this company in Iowa that had been making cement trucks was purchased by this bigger company. The bigger company had a very, very sophisticated military division that made a lot of our, well, they had, when they were trying to replace the Humvees and stuff in Iran and Iraq, this company had like a $40 billion contract over a couple of years to make all the MRAPs, okay? I'm not going to tell you the name of the company, but you can look it up if you want. But they're sort of a world apart from the military division and all the 50 or 60 other little mom and pop organizations. And for these 50 or 60 other little mom and pop organizations, they had, at one time, they had one engineer for all 50 or 60 of them. You're making vehicles here. You know how many thousands of engineers General Motors would have, or Ford? Well, that's why these little moms and pops could compete with General Motors or Ford or somebody and making a cement truck. They could buy the basic, the engine from Cummins or Caterpillar, and they could slap it onto a frame that they buy from somebody else, and they could buy the hydraulics from somebody else. They didn't have to have an engineer. They had all their suppliers do the engineering for them. They go to a hydraulic supplier and say, oh, we need something that'll do this. And the hydraulic supplier would sort of engineer it for them and give it to them. But they weren't really engineering the whole vehicle. There was no one engineering the whole vehicle for these little moms and pops. They had a guy in Missouri or somewhere, but he basically retired. And they hired a consultant for a while, and he probably had plenty of work to do, I guess. And then he went somewhere or something, and so they had a lawyer, okay? And he decided to do the engineering, okay? So it turns out they could make these tanks, and they just made a nice simple little tank, just a cylinder of aluminum, and you had a dome, and it had some ports. You had to bring the and a flange on it. You had to bring the water in somehow, right? And they put a little weld here and a weld here, and they put a weld around here, just like you see over there. And they'd weld this up, and they didn't really, the guys in the shop, well, they'd been farmers, okay? They knew how to weld. And so they made a bunch of these, and then someone thought, well, maybe we ought to check and see, the lawyer thought, maybe we ought to see if there's any requirements on the design, some specifications for this. Turns out the cement trucks are regulated by the Department of Transportation because they have to go over the highways, right? Obviously. So he goes to the U.S. Department of Transportation. He says, we got this 55 or this 200-gallon pressure vessel. It's about twice the size of a home hot water heater tank, right? And do we have to have any special regulations? And the DOT gives him an opinion and says, well, that's not part of the vehicle that you use when you're rolling down the highway. That's something you use when you're stopped. That's sort of something like, we don't consider it part of the vehicle, and so we don't regulate that, okay? It's like kind of carrying a toolbox on your truck. We don't regulate toolboxes, okay? And the guy says, oh, fine. And then he looks himself, this lawyer, in the boiler and pressure vessel code, and it says that it excludes, well, there's some exclusions in there. And the way he interpreted it, this, even though it's a pressure vessel, it would be pressurized to 55 psi because they're going to use the air brake pressure. There's a compressor on the trucks with air brakes that runs at 55 psi. They're going to have 55 psi to push the water out of here so you can hose down things. And 55 psi is sort of typical pressure in a garden hose. Okay, so that worked great. They didn't have to have the extra weight of a compressor. They could just tie into something that's already on the motor of the truck. And they built these things, and they didn't go and look at what the boiler and pressure vessel code said. The boiler and pressure vessel code said, hey, if you got a hole in a plate, you just got a stress concentration of factor 3, you have to use a doubler plate. That's required by the boiler and pressure vessel code. But this lawyer determined, well, in his engineering judgment, okay, you don't need a doubler plate because the boiler and pressure vessel code doesn't apply. This is part of the exclusion. Well, we're not excluding science here, okay? We're excluding who regulates what. And he says, well, DOT doesn't regulate me, and I'm part of the exclusion in the boiler and pressure vessel code. We'll just keep building these things without any doubler plates, without any reinforcements, where the boiler and pressure vessel code. So we're going to ignore good engineering practice. Okay? We're just going to build these as cheaply as we can, and we're going to put them out there. Well, they did. They built 100,000 of them, and they put them out there. And aluminum, particularly in certain environments, can corrode, and they did sort of have a warning that if you, well, they said if you ever develop a leak, send it back to us and we'll fix it. Okay, it's kind of what they said. But a lot of these shops, they got their own welders or mechanics, and so people were welding on these things all the time. Well, if it had been come under a boiler and pressure vessel code, no one can weld on it unless they have an ASME stamp, which means they're certified as an authorized American Society of Mechanical Engineers repair station. Well, these cement truck companies don't have ASME certified welders or qualified welders, but these people didn't really know about that, and so they're welding on these things all the time. So one of these comes back for about its third time being welded on because it started leaking, and the guy did the weld repair, and then he takes some compressed air to check and make sure there's no more leaks. And he's supposed to be testing with 5 psi air, which is a typical way to test an oil tank for someone's home or something, because 5 psi, you're not going to generate enough pressure. Even if the thing does break open, it's probably not going to kill you. Well, for some reason, they didn't have a regulator on there, and he was using shop air at 100 psi. And he fills it up, and frankly, he should have realized it took a while to get up to 100 psi. Maybe he kind of had left it on there or something, went and did something else. But in any case, the thing blows. He's standing right towards the end cap comes off, and they find him 100 yards away up against a dumpster in 4 pieces. Okay, it's pretty gruesome so far as that goes. So a couple of us go down. One guy who was served on the boiler and pressure vessel committee looked at it. I looked at it, and we could see it was corroded and stuff, but it was basically an overload failure. And so we knew that it wasn't 5 psi air, and they later confirmed that. But we said, well, wait a second, there's no doubler plates here. What's going on? And that's when we uncovered all this stuff about the lawyer had been doing the engineering, okay? And he was reading the letter of the law, not the common sense of what's good engineering practice. Well, my friend from California who used to be on the boiler pressure vessel code committee, he said, well, as a professional engineer, he knew that this type of vessel was actually required to be inspected in Pennsylvania, which is where this occurred. The boiler and pressure vessel code is really written not as a federal law, but all the 50 states have incorporated the boiler pressure vessel code into the law in one way or another. And so he says, under Pennsylvania law, it doesn't matter whether it has to have an ASME stamp. The state of Pennsylvania says any pressurized vessel, not the ones including the ones that are excluded by ASME, has to be inspected by someone on what they call the National Board of Pressure call it the National Board. I can't remember the full name, but it's the National Board of Inspectors. And there's probably a few hundred of these people who spend their lives going around and doing independent inspections for insurance companies and other people. We used to have them come around MIT to the compressed air tanks. Every year they'd have to take shut it down, take a nipple off, take a flashlight and a little mirror, look down inside and make sure they hadn't corroded the welds. Something changed in Massachusetts laws, and that never gets done anymore. So when you're standing around a big compressor tank at MIT, be careful, okay? It may not have been inspected for a while. But in any case, and they do blow up every now and then, even if they're built to ASME. This one wasn't built to ASME, and Roger said, I got a problem. These should be inspected under Pennsylvania law. And so he had an ethical responsibility to go and tell some of his friends who were on the national board. The national board is not the same as the ASME board, pressure vessel board, but he knew all these people because the two of these sort of fit together. ASME code is for building the vessel. The national board code is for inspecting the vessels after they're in service. So he knew all these people. So he goes he's at some meeting, and he's at a cocktail party or whatever. He tells his friend about there are some of these trucks out there and they haven't been inspected on a regular basis, and people are doing repair welds on them. And he thought that these should come under the national board and should be required under many state laws that they be inspected, whether they got an ASME stamp or not. That they don't have to have an ASME stamp in many states. And the guy from the national board, he says, well, how many are there? And Roger says, well, about 100,000. And the guy said, 100,000 of these would take 100 inspectors. Well, they only had a couple hundred inspectors. They didn't have enough people on the National Board inspectors to be able to take care of this problem. Okay? So in any case, now, how could they get into this problem? Well, it got even worse because when these things were brand new, they actually had a failure. They were doing hydro tests to pressurize them, brand new tanks in Iowa, and one guy was using, we don't know exactly what pressure air, but one of them blew up and took his legs off. He became, a double amputee. And that was before this guy got killed in Pennsylvania. And the company had looked at it, and the attorney, using his best engineering judgment, decided it was sort of a one-of-a-kind problem. Okay? It had nothing to do, well, he didn't even know what a doubler plate was. So this is a story to tell you a story, but there is a moral to it in the sense that I see this once or twice a year in some failure I'm doing, where people have decided they don't want to pay the overhead of engineering. Engineers cost too much, and we got guys in the shop who can design this, okay? And that's how you get in trouble a lot of times, when you don't have any technical input to your designs. Anyway, here are some other aluminum designs for welds. In this case, they put intermittent welds on a plate on top of a plate. So you're really making a T-shaped plate, but you've really got this flange here that gives you lots of weld area. This is good, better, and best in terms of, here they've scarfed the edges to reduce the stress concentrations and taper the stress at the end. Here are some other things where you end up with bigger weld areas than you would often end up with if you were welding things in steel. Okay, here's actually the more common one. In steel, if you were trying to weld a pipe onto the web of a steel I-beam, you just put the pipe up there, cut it at an angle, and put a little fillet weld around the tube. In aluminum, because you can't get the full strength, you actually weld on a gusset plate, and then on the gusset plate you slit the tube, and you end up with 4 long welds, fillet welds, whereas before you would have just had a simple little elliptical weld going on steel going around a tube. A lot more expensive, but it's a more expensive structure so far as that goes. Here again, scarfs, so you taper your stresses, things that we don't usually have to do in steel. So there's design of aluminum weldments certainly requires a lot more thought for the stress and load paths than we usually have to worry about in steel. Steel, you just sort of slap it together, and usually it holds. Now there are a number of types of defects that you can have in aluminum, but it turns out most of them, or many of them, are not terribly harmful. We do have a problem with hydrogen, and here's the solubility of hydrogen as a function of temperature. With steel, when it melts, it has a very high solubility. What's the units here? Cubic centimeters of hydrogen per 100 grams of aluminum. That's one of the things we use with steel, a measure of how many cubic centimeters dissolve in 100 grams of the metal. So there you go from 0.5 down to, I guess this is a semi-log plot. You go down to a factor of 10, basically, more than a factor of 10, factor of 10, 12, or 15. Drop in solubility of hydrogen. What that does is it gives you porosity. So you will never have an aluminum weld with zero porosity. There's always moisture around. Decompose the moisture into hydrogen and oxygen. You're going to get a few tenths of a percent hydrogen in the weld metal. Did this one actually tell me? This one, they had argon gas with no hydrogen. There's still a little bit of something because there's moisture on the surface, adsorbed moisture on the surface of the metal before you weld. Here you got 1/4% hydrogen in the shielding gas. Here you got 1% hydrogen in the shielding gas. And you get all this porosity. Well, it turns out there's an X-ray standard by ASTM for aluminum castings and welds, and it's basically just a bunch of X-ray radiographs. I bought my copy about 15 years ago and paid about $300 for it. You go buy it today, you'll pay about $2,000 for the exact same thing. Why? Because the code writing bodies have decided this is a good profit maker. Okay, they've jumped the prices of all these things. So I guess it was a good investment. If I knew anyone else who ever wanted a copy and was willing to pay for it. Anyway, you say, well, gee, that porosity. If you saw that kind of porosity in steel, it would be absolutely rejectable. In fact, this type of porosity probably is going to be rejectable in aluminum, but not really with good reason, just because it's sort of objectionable. It shows a complete lack of care in making the weld. If you actually look at, I mean, in steel, you can get hydrogen embrittlement. There is no embrittlement with hydrogen in aluminum. There's only porosity. And people have done extensive studies looking at the percentage of porosity on the fracture surface versus the tensile strength. So this is full strength, 50 KSI. And if I have up to 40% porosity, I lose 40% of my strength. So it's just like aluminum is a fairly ductile metal, no hydrogen embrittlement. And my strength reduction is directly proportional to the volume fraction of porosity. I can have 5% porosity. All I lose is 5% of my strength. It's not usually a big deal. However, when some failure occurs in aluminum, someone says, oh, there's a pore there. Okay? So, yeah, so what? You do lose more of your elongation. It's a little steeper loss in elongation, so it doesn't stretch as far. So one time I had a guy who was in a tree stand somewhere, well, actually it must have been somewhere near White Plains, New York, because that's where the trial was, and it was an cast aluminum turnbuckle that was one of the things that was holding this tree stand. You know what a tree stand is? You know, some guys are going to go out there with a bow and arrow or a rifle, go out and shoot little deers, shoot Bambi. Okay, he sits in the tree, freezing in the fall, just so he can shoot Bambi. Okay, so anyway, so this guy fell from the tree stand, hurt himself, and the turnbuckle was broken. So, and someone looked on the fracture surface and they found 4 pores. Woo! I should be concerned, I guess. So it actually went to trial, and it was sort of interesting. I was in the witness box, and it was sort of a table that was bigger than this table. It's about twice the size of this table. And I was trying to explain, because the other side had gotten up and put these pores in the scanning electron microscope and made them about the size of basketballs, right? Okay. And which is a typical trick. And I had to explain to the jury how big these pores were. And I did explain in words this kind of graph that the loss in strength is roughly proportional to the area of the pores. And if I had 5% area loss, I'd have 5% strength reduction. And I said, if I took this table and considered it the size of the fracture surface, magnified fracture surface, it was the equivalent of putting 4 ping pong balls on the table. And it was. I had done the calculation, okay, for the size of the... That was the way I got the message across, and we won the case, because the jury, I said, you know, I had pointed out, 4 ping pong balls on something the size of a desk was not enough loss in area. It was probably less than 2% of the strength. This turnbuckle still had 98% of its strength. That's not why the turnbuckle failed. Actually, the turnbuckle was also bent, and so it turns out he probably fell in a way that caused the turnbuckle to bend, and their turnbuckles aren't designed to take a big bending load. So anyway, but a lot of this is when you get into well, you don't have to be testifying in front of a jury. Just explaining it to a layperson, you have to come up with something that they can understand. They look at this thing, a picture in a scanning electron microscope, and the pore is huge. To relate to the patient. You've got to get things down to something they can relate to. And I actually find most of my chemistry examples come out of the kitchen. Okay, I usually find some analogy that has to do with kitchen, cooking and things. If we look at other defects in aluminum welding, because aluminum has this 6% volume shrinkage, when you stop welding and you have a little casting right here at the end of the weld that's shrinking, right in the center you'll get enough shrinkage that you'll develop what we call crater cracks. So the little decreased crater, so everything's shrinking around it, large tensile stresses, and you'll develop cracks. So here's an end crack. Whenever you finish the weld, you often, well, if you don't have the right technique, really you'll get a crater crack. What you should do, if the guy's welding along and moving along, they at the end, before they turn the power off, they should stay steady. They should stop and melt extra aluminum so you form a mound and don't leave a concave crater. Okay, you put extra metal in there, and now when the thing solidifies, it has enough, in casting we call it, has a riser head to feed molten metal to fill the region that's solidifying and shrinking. Okay, so you're just making a little casting. You just have to create a riser, a little head of molten aluminum. So this is actually poor technique to end up with crater cracks. It's easy enough to get rid of, it's just welder technique. Okay, another thing is aluminum has problems in that it has a very tenacious aluminum oxide skin. That's what gives it good corrosion resistance, but that aluminum oxide skin is actually a hydrated aluminum oxide, so it doesn't really melt at 2000 C. Maybe it only melts at 1500 C, but given that the aluminum alloy melts at 550 to 660 C, depending on how pure it is or how highly alloyed it is, that's a big temperature difference. And so when you melt aluminum and there's very much air around, you'll form this oxide skin, and the aluminum doesn't really flow. It just gets this oxide skin, and you end up something looks like